In today's lecture, we are going to solve a very important problem. Actually, we have to show or to prove two important results. The first result is phi equal to minus E dot R, where you know phi is actually the scalar potential and the vector potential A is equal to 1 over 2 B cross R. Here actually R is the position vector and you know E and B are the electric and magnetic field vectors. In fact, these two results holds only when the electric and magnetic field vectors are uniform. So you can say that in a uniform electric and magnetic field, how we can express the scalar potential phi and the vector potential A in terms of these uniform field vectors, we have to discuss it. Okay. In fact, these two results can be derived by a very simple calculation. You can easily understand it. So be serious and watch the video seriously. Definitely everything will be very clear to you. So now let us start to prove this first result, that when the electric field is uniform, then the scalar potential phi will be equal to minus E dot R. We have to show it. Okay. As you know that this electric field vector, when expressed in terms of its rectangular components Ex, Ey and Ez, then you can easily write that this E is simply equal to Exi plus Eyj plus Ezk. Okay. Now let us try to find this expression E dot del R. We have to find it. You will see that after finding the value of E dot del R, this will be simply equal to E. But how you can say that this E dot del operated on R will is equal to E? Let us try to understand it. You know, this vector E can be expressed as Exi plus Eyj plus Ezk. And dot del. Del, you know, this is just a gradient operator. So in Cartesian coordinate, instead of this operator del, you may write I del del x plus j del del y plus k del del z. And this is operated on the position vector or the radius vector r. Okay. Actually, the page has been turned, but don't be worried. This will be just okay. You can see this is now okay. And we will solve our problem very easily. Okay. Now see. Now you know that when we will take actually the scalar product of this Exi plus Eyj plus Ezk with I del del x plus j del del y plus k del del z. As in a scalar product, you know that whenever the scalar product of two dissimilar unit vector will be taken, that will be simply 0. So only the similar term is non-zero, and so the product will be what? This will be Ex del del x and I dot I will be 1. So the first term will be Ex del del x. But if you will take the scalar product of this Exi with j del del y, then you know I dot j will be 0. Similarly, j dot I is 0, k dot I, k dot j, all these are 0. So only the similar term will remain non-zero. And so you can see that this product will be what? This is Ex del del x plus Ey del del y plus Ez del del z. You can check it. You can check it. And this is operated on R. Now, you know that this position vector R is simply equal to Xi plus Yj plus Zk. Now, operate this operator on this vector R. So, in the first term, this will be Ex del R by del x. What will be the first term? Ex del R by del x. But instead of this R, I have written here Xi plus Yj plus Zk. Similarly, in the second term, you will have Ey del R by del y. And again, instead of r, I have written xi plus yj plus zk. And similarly, you can write the third term. Now, in case of partial differentiation, when this operator del x will be operated on xi, what will be your result? Since I is a constant unit vector, so it will be outside of the operator, and del x by del x will be equal to 1. So the first term will be ex del x by del x I. But del x by del x 1, so this will be simply exi. But if you will operate this operator del x on yj and zk, these two terms will be 0, because when y and z will be differentiated partially with respect to x, the result will be 0. And similarly in the second term, there will be del y by del y1 and other terms will be 0. So the second term will be what? This will be eyj. And in the last third term, del z by del z will be 1 and other terms will be 0. So the last term will be simply ez del z by del zk. But del z by del z will be 1. So this will be ezk. So what will be the result? The first term will be simply exi, second term will be eyj, third term will be ezk. So you can see I have written here that this E dot del R is simply equal to exi plus eyj plus ezk. But you know that this exi plus eyj plus ezk, this is equal to vector E. So we can easily write that this expression E dot del R, this is equal to vector E. Okay, I hope you have understand. Now you can see, since our electric field vector is uniform, it is constant, as I have told you earlier, that the result which we have to prove that holds only when the electric and magnetic fields are uniform. So you have to consider that this electric field is uniform, it is constant. And if it is uniform, this expression E dot del R may be written as del E dot R. What you can write? You can write this E dot del R equal to del E dot R, because E is uniform. Okay. Now in case of the uniform electric field, or you may say that in case of electrostatic field, you have studied electrostatics in your lower classes, and where you study that the electrostatic field E is simply equal to negative gradient of electrostatic potential phi. That is, E is equal to minus del phi. Now compare these two equations, 3 and 4. You can see in equation 3, E is equal to del E dot R, and in equation 4, E is equal to minus del phi. So when we will compare these two equations, we can easily observe that in equation 3, this E dot del R is at the place of minus phi. So we can say that this phi is equal to minus E dot R. How easily this result has been obtained, you can see. But this is a very important problem for your examination. So you can see the video seriously, write down it in your notebook, and very easily you will be able to write this solution of this problem in your examination. Okay. Now we will see another important result. See here, in the second problem, we have to show that the magnetic vector potential A is equal to 1 over 2 B cross R. Okay, here B is actually magnetic field, And again I am telling you that this result also holds when this magnetic field vector B is uniform. Only then this result will hold. Remember. Now, to prove this result, Let us start with a well-known vector identity. You have definitely studied in vector calculus this vector identity, and this is curl of the vector product of two vectors A and B, curl of A cross B. If you have not studied this, remember this, because whenever you will study it in vector calculus, even after that you have to remember this formula. Okay, so remember that curl of A cross B is equal to A divergence of B minus B divergence of A plus B dot del A minus A dot del B. Remember this vector identity. This is a very important vector identity. Now, if we write instead of A equal to B, it means if we recognize that this vector A is equal to the magnetic field vector B and B is recognized as R, then what will be our result? It means you have to write B instead of this A. B means magnetic field vector B, capital B. And instead of the another field vector B, we write the position vector R. So after this substitution, this equation 1 will be what? This will be simply curl of B cross R equal to A divergence of B. But instead of A, we will write now B. So this will be B divergence of R minus R divergence of B plus R dot del B and minus B dot del R. Okay. Now see, as I have told you that this result which we have to prove, this holds only when magnetic field is uniform. So if the magnetic field will be uniform, you will see that two terms in RHS will vanish. That will be 0. And what are those two terms? You can recognize it. So for uniform magnetic field, for uniform field B, uniform magnetic field B. Uniform means constant. You know that the divergence of a constant vector is always 0. Not only divergence, but gradient of a constant vector, gradient of a constant scalar, divergence of a constant vector, curl of a constant vector, all these are 0. Since B is here constant, so we can say that divergence of B, this will be equal to 0. Because divergence means simply partial differentiation with respect to a space coordinate. And when you will differentiate this constant field vector B with respect to a space coordinate, this will be simply 0. Okay. And also you can see this R dot del, this is also a differential operator. R dot del is a differential operator. And when this operator will be operated on a constant field vector B, again the result will be 0. Because R dot del is what? This is simply x del del x plus y del del y, y plus z del del z. And this operator is operated on a constant vector B. So this result will be also 0. So you can see in RHS of equation 2, this term vanishes, this becomes 0. This term also vanishes, this becomes also 0. So the remaining terms are B divergence of R, that is this first term, and the last term B dot del R. So you can write this curl of B cross R equal to what? You can now write it. Therefore, we can write that curl of B cross R, curl of B cross R. What are the remaining terms? You have just seen that these are B divergence of R and minus B dot del R. You have just seen. Okay? This is. Now let us say this is your equation number what? This is equation number 3. Let us assume. Okay. Now, you know that this divergence of R will be what? Divergence of R. It and vector R, you know, is defined as xi plus yj plus zk, you know. So divergence of R will be simply equal to del x by del x plus del y by del y plus del z by del z. And this is 1 plus 1 plus 1, that is 3. Therefore, you can say that divergence of R is simply equal to 3. You should remember it. There is no need to calculate this divergence of R like this. This is a very important result, and definitely its value should be in your mind. You can write it directly. Now, what will be the value of B dot del R? B dot del R, can you say? If you will give a stress on your mind, you can say what will be this. In fact, this B dot del R, this will be simply equal to B. But how? I have just proved it. Remember, I have proved it for the electric field vector. You can see. In case of electric field vector, you have seen that I have shown here that this E dot del R is equal to EXI plus EYJ plus EZK. And therefore, E is equal to E dot del R. You can see this result. See this result. What is the difference? Only there is vector B instead of vector E. E is also a uniform field vector, and B is also a uniform field vector, so the result will be not different. So if E dot del R is equal to E, you have proved it, you can easily say that B dot del R will be also equal to B. So again, there is no need to prove it. I have already proved this result. Have you understand or not? B dot del R, like that expression for E, you can write this is equal to B. Now, let us substitute these two values in our equation 4. So, you can write this curl of B cross R will be what? You can see curl of B cross R. B divergence of R, but divergence of R is 3, so this is equal to 3B, okay? And minus B dot del R, this is what? This is simply equal to B. So this is equal to 2B. What is this? This is 2B. And therefore, you can say that this vector B is equal to what? This is 1 over 2 a curl of B cross R. Okay? This is curl of B cross R. Or you may also write it, this is 1 over 2 del cross B cross R. Okay? And say this is your equation 4. Now, you have studied the concept of electrodynamic potential, and you have seen that the magnetic vector potential A is defined in terms of the magnetic field vector B. So we know that the magnetic field vector B is equal to what? This is in fact del cross A, okay? Or equivalently you can say that this is curl of A. Curl of A. Now let us compare these two equations, equation number 4 and equation number 5. You can see B in equation 4 is equal to 1 over 2 del cross R. Since 1 over 2 is a constant factor, so this result may also be written as del cross 1 over 2 B cross R. You can write, because 1 by 2 is a constant, so it can be written inside the bracket. Inside the this operator. So now compare equation 4 with 5. You can see at the place of curl in equation 4 and 5, in equation 4, also in equation 5 there is curl. So del cross is present in both equations. So definitely this vector A must be equal to 1 over 2 B cross R. So comparing equation 4 and 5, we can easily say that the magnetic vector potential A will be equal to 1 over 2 P cross R. So comparing these two equations, what will be our result? The result will be the magnetic vector potential A is equal to 1 over 2 B cross R. And this is the result which we have to prove. So you can see that this magnetic vector potential A in case of uniform magnetic field is simply equal to half of B cross R, where B is the uniform magnetic field and R is the position vector. So these two important problems we have solved very easily. You have to remember only a vector identity for curl of A cross B, and starting from that you can easily prove that A is equal to 1 over 2 B cross R. I hope you have understand these things very easily, and as I have told you, these results are very important for the objective problems in your examination too. Okay.